So, first of all, let's decide what is a compound inequality before we learn how to solve and graph them. When we have two simple inequalities that are combined into one statement, we call it a compound inequality. What's a compound word? This is English now. What's a compound word in, you had to have been taught this in English.
Two things put together.
Two words put together. They're words that can stand alone, but when you put them together, they make a compound word. Guess what? Didn't. Didn't is actually a contraction. And when we write it as did not, we don't put it together as one word. So did not is really actually not a compound word. Anybody think they do know one?
Compound.
A compound word. Into.
Does it have ED, ES?
No. So a compound word is two words that can stand alone, but when you put them, they can also be put together and made into one word. Okay? So Andrea said into. So in is a word, to is a word, into, put it together is another word. Anyone, any is a word, one is a word, but put it together. Now, there's no space between, they just put them together and becomes a compound. Same thing with math. There's no such thing as a compound inequality when we put two inequalities together. So we've been working with what are called simple inequalities. When we put two of them together, they become what the result is called a compound inequality. And there are two types, okay? We have the and type. Would you circle that just so that it stands out there for us? And when we talk about the and type, that's an intersection. So when we, intersection meaning the combination of the two of them together. And when we have a compound inequality of the and type, usually the graph, I want you to draw a graph over here. The graph, so we're going to have two endpoints on our compound inequality graphs. We're going to have two. So they can be open or closed circles. I'm just making them both of them closed. We'll decide when do we shade them in and when don't we. And when it's a compound and inequality, typically this is where it is shaded, in between the two endpoints. So maybe make those circles bigger so we can see. So it is usually between 2 points. When we graph our solution, usually it's between two endpoints. It's an intersection. Okay, the other type of compound inequalities, there are only two types. The and type, the other type is called the or type. Would you circle that? The or type is the union of them. The union of them. And the graph for these still has two endpoints. And again, we have to decide whether those endpoints should be shaded or not, but for just now, we'll just shade them in. It's usually outside the 2 points, going away from it, okay? So usually the shaded region goes outside of the 2 points, or we could say opposite 2 points, okay? So, kind of like, typically, this is typically what happens, okay? Usually the graph, when we graph an or compound inequality, it's the shaded part goes opposite from the points instead of between the 2 points, okay? Now, let's kind of put this into, like, so that we can kind of get an idea of what do we mean by intersection and union, okay? Let's think of something in real life. Let's talk about you know, like you're under your parents' roof and they make the rules and they tell you what you do and don't need to do. Whoever is in charge of you gets to call the shots, don't they? So if you really want to do something this Saturday, and they say to you, you need to clean your room to their standard, of course, and I want you to clean, you know, maybe you have cats at your house. I want you to clean the cat's litter box. Then you can do what you want on Saturday. Clean your room and Clean the cat's litter box. What if you only clean the cat's litter box and you say, I'll just close the door to my room and maybe run on touch? Are they going to probably let you do what you wanted on Saturday? No, because it was an and, wasn't it? Means you got to do both. Yes, Jim. I have.
That or some people just shove their stuff under their bed.
Yeah, call that cleaning. Right?
Or in their closet.
Yeah. But when it's an and, you would meet both of the things that they want you to do, or you're probably not going to get to do it. So in other words, you don't have a choice. So you have to do both. You can't just say, I'm just going to do one or the other. Okay, the ors are like this. This is the way you might like it. You can do what you want on Saturday if you clean your room or you clean the cat's litter box. Now you get to choose, don't you? You have two things to choose from, and as long as you do one of them, you're going to satisfy them, and you get to do what you want on Saturday. So that's kind of how these are. We need, when we talk about the solutions for an and compound inequality, the solutions have to make both things true. It has to satisfy both. When it's an or, it only has to satisfy one or the other. So it can come from either place. So we're going to start with the and compound inequality. So let's circle that again. Let's solve some and compound inequalities. When we're solving these, here's what's really important. You need to underline this. Do the same thing to all three regions. Do the same thing to all three regions. There's going to be three kind of like sides, which we kind of typically are used to solving equations and inequalities where there are sides. There's two sides. This is going to have regions, and there are going to be three of them. And our goal is to get x alone in the middle. So we need x alone in the middle. Okay? So our goal is still to have x by itself. It's just not going to be on one side or the other. It's going to be in the middle this time. So here's our first one. This is how it reads. -5 is less than x plus 1 and is less than 2. So this is an and one where it has to satisfy both, kind of like two things at the same time. So here's our regions. -5 this right here is a region. X plus 1 is a region. 2 is a region. We're concentrating on getting that x alone in the middle. So what are we going to have to do to all three regions to get x alone? Subtract 1. We need to subtract 1. That's how we will get x alone. If we do it there, we got to do it in the other regions also. We have to do it in all three regions. Okay, what's -5 subtract 1? -6 is less than. We didn't do any multiplying or dividing, so we don't have to worry about do we have to switch it. X is now by itself. Is less than. What's on the other side? 1. Okay, this is, right now, you can circle this. This is our solution. X is by itself. And here's what it says. To be able to be considered an x value, you have to be, x is in the middle here. I'm going to read it from the inside out. It says x has to be greater than, the number you pick from the shaded region has to be greater than -6, and at the same time has to be less than 1. So we're going to try and make a picture of that. -6 is smaller than 1, so -6 would come first on the number line. Here's where we don't have to use integer neighbors, okay? You get to just put these two endpoints on the number line. And then we decide, would -6 be part of the solution region? Is -6 greater than -6? No. So we'd have an open circle. Let's check out 1. Is 1 less than 1? No, so we have an open circle. What numbers are greater than -6 and at the same time less than 1? Give me an example of a number that is greater than -6 and it is less than 1. -2. 0, yeah. Numbers in between here, right? So where are we going to shade? In between, yeah. We're going to shade in between those two endpoints. Because those are the only numbers that satisfy both parts. Greater than -6 and at the same time less than 1. Anybody have any questions so far? Okay, what do you think we're going to do first then in number 2?
Make that negative minus into a plus sign.
Okay. So you're gonna, and then what else? You can't just make it into
And then make it a 1 into a negative.
Okay, so we can do that. Rename it. Change it to add the opposite. Okay. Now what should we do? Add 1. Yeah, we're working on getting the x alone, but it's going to take more than one step, isn't it? We need to get rid of the -1 first, so we'll add 1
To both sides.
to all 3 regions. We don't have sides anymore. We kind of got regions. Okay. So to all 3 regions, we're going to add 1. So we'll, in the first region, what do we have? 9 is less than. What do we have in the second region? 3x. What do we have in the third region? 12. And notice our symbols didn't change at all, did they? Okay. What should we do now?
Divide the 3 into all regions.
Okay, let's say it right. Divide all 3 regions by 3. Good job. 9 divided by 3. 3x divided by 3. 12 divided by 3. Okay, go ahead and write what you think is the final answer here, the solution, on your papers. And then we'll see if we agree. Do we agree? Okay. What is that? What's that saying the solutions are? What is that really saying? X, the part that we're going to shade, has to be what?
Greater than 3.
Greater than 3.
Or less than or
No,
equal.
not or.
And less than or equal to.
And greater than 3 and
Less than or equal to.
less than or equal to 4. So it's kind of like a little tight window there, isn't it? Between 3 and 4. Okay, but then the next thing we got to decide is are 3 or 4 included. So the only thing we have to do right now is this. Put our 2 locations. We don't need any integer neighbors in these compound inequalities. What should we do with our circle at 3? Shade it in? No, because 3 is not greater than 3.
You would shade
How
it
about
low.
4?
Shade it.
Yeah, because 4 is equal to 4. It isn't less than 4, but it satisfies the equal to part, doesn't it? Okay, and then what other kind of numbers do satisfy both situations?
3.
Like 3 1/2,
3 1/4.
3 1/4. All the numbers between 3 and 4? Yeah. So
Yeah.
let's shade those guys. Okay, these are the ands. This is the, you know what, you don't get to do what you want on Saturday unless you do both the things. So it's got, you gotta satisfy both parts or you don't get the solution you want. Anybody have any questions before we move on to the OR types?
No.
Okay, let's go to the back side then. Solving OR compound inequalities. Let's circle that. OR, as you remember, it has to satisfy one or the other. Don't have to do both. So solve each of them separately, okay? So these are not going to be written together. You know what, I'm like blanking. Yeah, that is right. It doesn't look right today. Separately. Do I have that spelled right? Mm-hmm. Okay, good. For some reason, it just does not look right. Solve each of them separately and then combine their solutions on the graph. In other words, you get to show this is all the possible places it can come from, okay? So we have in number 3, we have 2 simple inequalities, and notice what's in between them, the word OR. So we have a simple inequality, but they are working together. They're a compound inequality, but we cannot write them with the x in the middle when they're an OR, okay? So we're going to solve this one by itself. We'll solve that one by itself. We'll bring down the word or and put between their solutions, and then we will graph it. Okay, what are we going to do in this simple inequality?
-2.
Okay, we'll subtract 2.
Section.
Okay, subtract 2 from both sides. Now we can talk sides again because we have a simple inequality. There aren't 3 regions, are there? And now we have our x alone, and we have x is less than,
2, 10.
okay? And then this one, what are we going to do in this one?
You would make that negative, that minus sign to plus, and then make that 5 into a negative.
Yeah, that's one thing you could do. You could rename it as x plus a negative 5 is greater than 9. And I like that Adam,
Greater than or equal to.
greater than or equal to, thank you. That Adam just stays in that habit because it's, good habit to stay in because they get tricky sometimes. So now we're going to do what to both sides? Add 5, okay? So x is now alone, like we want it, is greater than or equal to 14. Okay, here's what I want you to do. I want you to rewrite both of those, bring them together with the word or between them. So x is less than 10, or x is greater than or equal to 14. So for the or ones, we have to write the word or. And I want that on every paper, okay? Okay, now what did it say? Combine their solutions on the graph. So bring them together, okay? So this one says, we've got endpoints of 10 and 14. What should we do with our circle at 10? Leave it open? Yeah, we should leave it open. What should we do with our circle at 14? That one should shade in because of the equal to part. Remember, this is an or one. It does not need to make both of them true. So you get to shade any part of this. So this one says shade numbers less than 10. So which direction will that be from 10? To the left. Make sure you make it look like you're shading. Fat line, fat arrow, it's shaded, okay? Or if it doesn't come from that region, it has a choice of coming from the other region, and the other region says x has to be greater than 14. So which way should we shade?
Right.
To the right. It gets to come from either part of this. It doesn't have to come from the ones that make both of them true. Do we have any that make both of them true? Do we have any numbers that make both true? X is less than 10. X is greater than or equal to 14. Can you think of any numbers that make both of them true? So, what does it have to? Does or mean you have to have something that makes both of them true? You get to choose from one or the other. Okay, you try this one on your own. Try this one on your own. I know you know how to solve simple inequalities, and we just practiced an or together, so I'm feeling confident you can do this.
I have a question.
Yes, sir.
When we're doing the graphing line, wouldn't we switch to the negative one so it's on this side?
Yeah, we sure would. That's a really good question and observation, Adam. In other words, you know what I think it would be probably useful to do is when you're writing them with the or between them, why don't you put them in the order that they're actually going to show up on the number line? So when we're writing our solution that we're going to circle, let's have them trade places so that we don't mess up our number line. So we all should have ended up with the first one solving to be x is greater than or equal to 3, and the other one, x is less than or equal to negative 1. Could anybody tell me why we don't switch the symbol in this second one? There's a negative involved.
Because you're not dividing by a positive.
You're not dividing by a negative, you're dividing into a negative, aren't you? Not by a negative. Okay, so now we can graph this one. Remember, we only need the endpoints. And Adam observed, you know what, -1 comes before 3 on the number line. Don't mess that up. Should -1 have a shaded circle? Okay, how about 3? Should it have a shaded circle?
Yes.
Okay. Okay, which numbers are less than -1? To the, Holly's pointing back there to the left, yeah, to the left. Headed that direction. Okay, which numbers are greater than 3? To the right, yeah. Okay. Here's what our solution, the circle part, our algebraic solution should look like, our graph that represents it. Okay, let's just do one more together, and then we should be ready to start on that fairly short homework assignment that you have. Okay, so what are we going to do in this one? The 3x minus 2 is less than 7. What are we going to do? Samuel, you tell me the first step I want to make.
I make 3x plus -2.
Okay. Sydney, you give me the next step.
Add the opposite, like
So what would the opposite be? We already changed it to add the opposite, so now what are we going to do? Add what?
2.
Yes, add 2. And now we should have 3x is less than 9. Seth, what's our next move going to be? Okay, divide both sides by 3. Thank you for saying that properly. And we have x. Do we have to switch our symbol? No? Okay. Every time we multiply or divide, hopefully we're taking the time to ask ourselves that question. Okay, there's our solution for that part of the inequality, compound inequality. Now we have to solve our other one. What's our other one? What are we going to do? Preston?
On the other side?
Yep.
Add the opposite.
So like that? Whoops.
Yeah.
Don't be giving that an equal to bar when it doesn't have one, huh? Okay.
We make them to add the 8 to both sides.
Okay, add 8 to both sides.
And then it would be x is greater than 7. Yes,
It doesn't sound very convinced. Should we go with what
I'm
he said?
sorry,
Yeah?
I think 7, but
Okay.
I also think it's 6 at the same time
Okay.
for some reason.
No, it is 7. Okay, now when we write our algebraic solution, we don't get to just circle these two things and call it good. We have to do what? Which one, in what order would they come on the number line? Who's first, 3 or 7?
3.
3. So let's just do it that order in our actual solution. X is less than 3. What word?
X is greater than 7.
What word? What word? Or.
Or,
You don't get to leave that word out. X is greater than 7. There's our algebraic solution. Go ahead and graph that. Hopefully our graphs will look the same. Now I want to caution you. I said at the beginning of this that the ORs typically have this behavior where you shade opposite the endpoint. Doesn't mean it happens like that all the time. I said typically. Typically means most of the time, not all the time. So don't just automatically shade going out from it without asking yourself, is that the way I should be shading? This says shade numbers less than 3. This says shade numbers greater than 7. Be careful. They might trip you up sometime and have you doing something different. But typically this is what it'll look like. Just like the and ones will typically be between the two endpoints. Typically, but always check to make sure. Okay? Any questions?